Good morning, everyone. My name is Shyam. I'm an applications engineer with Analog Devices. And today I'll be talking about radio architectures in general, some design challenges that you face when designing a radio system. And most importantly, it's from an RF engineer's perspective, which is kind of removed from maybe what you guys have heard so far in the conference. So a different perspective. So I'll go over the certain trends in wireless communications, discuss some design challenges, discuss a few different types of radio architectures and some of the use cases that are most common to these kind of architectures. Give a comparison to our new transceiver, the 89371 versus the previous transceiver, the 9361 that you're so familiar with, I hope. And discuss some numbers because I can't be hand-waving too much. So we'll discuss IQ imbalance and some AGC specs with the new transceiver. Finally, some Q&A. All right, so before we get into some of the trends, you're all familiar with the SDR stack, but this is your traditional software-defined radio as defined by Wikipedia, and which we believe to be true. So the flexible RF hardware, ADC, DAC, channelization, sample rate conversion, all of that is your typical hardware setup. Then you have more hardware that does a lot of the processing. Typically, that's the baseband that you guys are familiar with, and that's where most of the GNU radio magic happens. But I really live here, or here. Now, the point I want to try to make is even though all of this stuff is important, that's where the modem, the baseband processing, and even if you are interested in cognitive radio processing, machine learning, all of those things, they all happen at these different layers all throughout. The final bits to RF or RF to bits, and the stuff that actually goes out and comes in, is determined by your transceiver. So if you don't have a good transceiver, you don't have a good representation of what you're looking at. Now, okay, moving back. So a lot was made about the flexible hardware during the panel discussions throughout this week. So if you think about reconfigurable radios, one of the key things that you need is the flexibility. That's what SDR brings to a radio design. So if you don't have a flexible piece of hardware sitting there, then you probably don't have the kind of flexibility that you want in software either. Okay. So should you really care about what's happening in the file layer? Maybe you don't. When you're sitting in the lab and you're testing a few different waveforms, you probably don't. But if you go out and design an actual system, you should. If really all that matters is RF to bits, are all bits the same? Do you even care? Probably not, because if your RF hardware, your front end itself is saturated, let's say with a blocker, how do you know that the bits that you're getting are an accurate representation when your ADC is saturated, for example? Right? And this is increasingly the case when you have more and more radios in the world out there. So to compare, let's say, an RTL-SDR, and this is not to denigrate the RTL-SDR. I own one, and I love it. But the comparison between, say, a really low-cost RTL-SDR and a user E310, which uses one of our products, is clearly in terms of performance. One is really more for hobbyist applications. The other one is for a little bit more serious of a hobbyist, I guess. So, and it's even made it to space, if the Virginia Tech guys are here. So, if you have RF everywhere and it's ubiquity, then you need to know what signals of interest mean and what blockers and jammers mean. And if you don't have an accurate representation of the spectrum, you end up losing what you try to gain in terms of processing gain and in terms of machine learning and cognitive radios. So just to keep you guys awake, that was all those 2 slides were to get you interested. Now, moving on to current trends in wireless comms, clearly everyone wants more data. You want to push more data through the air. For comparison, you take GSM or Edge, you're in the kilobits per second, but now with LTE Advanced or true 4G, you want hundreds of gigabits per second. And this drives demand for more bandwidth, that is more RF bandwidth, not just the digital throughput, which means more spectrum. Spectrum isn't cheap, so you can ask Verizon, AT&T, all of those guys how much they pay for a small chunk of spectrum, and they'll tell you it isn't. So the other thing that people keep talking about is MIMO, massive MIMO, even for future 5G products. It's from a software-defined radio perspective, there are challenges, but there are more challenges in terms of the RF signal chain as well. So if you're doing digital beamforming, you want to be able to do independent data streams and such. So that is just, I mean, I'll get into some more details in a bit, but just to give you an idea of what's coming. Okay, with the Internet of Things, machine-to-machine, communications, variables, what you end up having is a lot of spectrum congestion, and that means that you need to have some form of cognitive radio. That's where we're all logically headed, which means spectrum sensing, which also means more FPGA processing. Now, why am I saying all this? Because whenever these kind of topics come up, an RF engineer would obviously want to know what it means to him or her, and what it really means is less time to market, more reusable hardware, and a similar user experience as you move between different networks. And if you want to guarantee that in a very tight schedule, and this is again more of a commercial application, let's say, you really want something that is flexible in the RF front end and the physical layer. So, RF signal chain challenges, how people like me still make a living. Size, weight, and power. This was discussed yesterday as well by one of the speakers, John, if he's here. Yep. So why is this important? Everyone wants to scale down on their swap requirement so that you end up having less operating expenses, more battery life. Think about UAVs, for example, or your handheld spectrum analyzers. You really want to drive the cost down. So integrating different things into a smaller package helps, but it also comes with a lot of challenges like isolation requirements, for example. So when you have less band-specific stuff and more common platforms in which you throw in just a few different pieces of RF front end to iterate over different bands, you end up getting the swap decrease. So with digital beamforming, like one of the techniques that is thrown out there, this is from a Keysight webinar, is pre-coding and spatial muxing. Now, again, the whole focus here is on the stuff here, on the precoder here that happens in the baseband, but it really depends, or it hinges on the assumption that stuff here, the D2A, the mixer, the PA, your duplexer, whatever it may be, all of those guys are behaving as you first called it to. So you might do an antenna cal with a phased array to understand the phase delay in the signal chain. But if that changes over temp and over your frequency range, then you have to recal again, which is an overhead in terms of time and also in terms of throughput. So that really affects where you're pointed to. So if your phase change, let's say even 5 degrees over temp, you're basically, if you wanted to point here, you might end up pointing here. And that's a big deal for anyone who designs phase arrays. Okay. So spectral crowding in hostile RF environments. Now this is a pretty old graph. This is something I took from IEEE Spectrum magazine, but the point that I want to try and make is man-made noise is a problem, especially at higher frequencies and always in ISM bands for sure. So to compare like a rural area, that's the blue line here, versus the green line here, that is more of a city center sort of location, you see a general increase in noise floor. And this is mainly because of poor RF hardware. Therefore, you can imagine anyone trying to do actual communications in such an environment is going to struggle, is going to have a lot of blockers and interferers. To the point, this is something that, and this is again a testament to GNU radio that I was able to use it. So this is the 2450 Wi-Fi-ish band, and you can see I was really close to the ETIS guys when I did this. So a lot of stuff going on here. Now imagine that that is my signal of interest right there. If that's a, let's say it's a narrowband FM modulation channel there, right there. But I have interferers coming in all over me all the time. If I don't react to it, if my AGC doesn't get to it fast enough, then I'm really what I'm losing is bits, actual data bits. Just a small GIF to show you what that looks in real time with my poor GIF skills. All right, so again, spectrum sensing is important. You want to be able to sense the spectrum because you want to see who is the primary occupant or the secondary occupant and move along the white spaces if you're doing cognitive radio, for example. But there are some challenges there in terms of or some mitigation efforts that there, like beamforming or null cancellation or null steering. All of these really add more and more processing requirements on the PHY layer. But they don't take away anything from an RF front end either, because you still need the kind of performance that you expect from a really great RF transceiver on top of all the added overheads in terms of processing and latency. All right? So what am I talking about in terms of RF metrics anyway? So mostly dynamic range, linearity, isolation, bandwidth, sensitivity. Bandwidth here could mean data rates as well, just to name a few. Now, here's the problem statement. You have all of these things converging on a realizable problem, which is the PHY layer having to do a lot of heavy lifting. Now, how do you combat it? You still want high performance, more and more bandwidth. You want all of those things. So why not move some of the processing requirements away from like the baseband and into the transceiver, or to kind of distribute the whole overhead that you need. So self-calibrating PHY is not new. We have had digitally assisted analog for some time now. But where you do it and how you do it and the kind of radio architectures that you could use to increase the benefits that you get from self-calibration is what we will discuss next. Another way of looking at it is to not just have custom digital do some of the DAA stuff, but also to add like a microcontroller or a microprocessor within your RFIC so that you have firmware flexibility. You can just push in a new firmware upgrade and boom, your performance goes up by 10 dB, let's say. Or you do bug fixes. You also want something that is low latency, and this has come up quite a bit in the past few days as well. If you try to do all of your processing at one centralized location, you end up having to communicate between these different layers, and that adds overhead and latency. And you want to be able to do it in different parts of the signal chain to kind of minimize that, especially if you go with let's say the future of communications is really low latency protocols. This is ever more important. So with that, some radio architectures, which is really all about partitioning, I would argue. So this is a typical physical layer for a communications guy like me. You have the baseband processor that does a few of these functions. You have the digital front end that does the digital beamforming, crest factor reduction, digital pre-distortion, pushes that into the RF transceiver, and out goes the bits that you want in the form of RF. Now, there are certain cases where you can get away with this, but we'll get to, let's say, a different argument in just a bit. To give you more of a historical context, discrete converter-based IF solutions usually look like this. You have multiple stages that mix down into an IF and then convert it to an ADC. The ADC converts it to INQ bits. Let's say you have the baseband that does digital down conversion and up conversion, however the case may be, and gets you a lower data stream INQ data that you push out through your USB or Ethernet connector. Now, these are good as far as the sampling rates are concerned, and if you're really concerned about a really small chunk of bandwidth, this is fine. Or if you want to do some very specific type of superhead type receivers, which I think is on demo at his booth, you could probably do that. But what happens here, though, is, and what I'd like to call your attention to, is all of the band-specific stuff that you end up having to put into your hardware. Now, you could put in as many bands as you want. You could design a broadband stuff network if you want, but it comes at some design trade-offs, and you have to realize that when you design your whole entire system. If you want something that is truly flexible, this is probably not as ideal as something we'll discuss soon. The other thing to consider is digitally assisted analog exists for ADCs, has existed for a while. But it happens on the ADC for a single chip that might have at most 2 converters. But the baseband processor has to look at the whole system and figure out if the system requirements are met. And to illustrate the point further, let's look at a typical PCB architecture for one of the dual channel ADCs that we have. Component tolerances, PCB tolerances, manufacturing tolerances, all of these things add to your IQ imbalance. And you have INQ paths, you have mismatches, all of these things combine to give you poor IQ balance, which has to be combated again at the baseband processor. Now, you have the ADC doing its DAA magic, but you also need to do some baseband processing to get really good IQ data that you can use. So, zero IF solutions, or direct conversion architectures, typically look like this, where you have an LO that is close to the RF, single mixing stage, push your data in to your ADC, you get INQ data. Now, this is possible when you can synthesize the center frequency in RF. It also enables integration, which in turn drives the swap cost down. It so integration also enables you to lower the power requirements that you need for the entire system, even for your chips. But also notice that the amount of frequency-dependent filtering, let's say, is much reduced as opposed to the discrete converter IF architectures. But it doesn't come for free. You have issues that are particular to zero IF, in terms of LO leakage or DC offset, depending on which side of TX-RX you are. You also have images, which are INQ imbalance presenting due to gain or phase imbalance or quadrature skew. So let's say these were your desired points for your constellation, but you ended up getting actually receiving these points. That means you have some gain error or an offset error if you just move it up, or a phase error if you just rotate it. This is actually a little bit more than phase error. So all of these things need to be combated because, I mean, this is your desired signal. That is your undesired sideband. And if there is, let's say, a smaller desired signal right there, you're basically creating an image that sits on top of it. So you're losing data right there. To IQ imbalance, this is what we use in terms of a metric to decide whether you have good IQ balance or not. So that's the error vector magnitude. That's your desired constellation point, but that's your measured point. You have a magnitude error and a phase error, which is typically expressed in percentage or dB as the EVM. So you could do IQ imbalance corrections or impairment corrections at the baseband processor, but you have to think about the overheads in terms of the actual processing required at the baseband and also the latency requirements. So it may not be as much of a problem in terms of the IQ balance, but latency itself is a major concern when it comes to designing an entire system. To illustrate further, let's say you take the 9361 datasheet and you look at this particular graph, which shows you RX EVM or receive EVM over interferer power levels. Obviously, as your interferer power level increases, you have poor EVM, but this lets you decide whether you can use your data appropriately. So like a 20 dB EVM may not be great, but that may be good enough if you have good interference cancellation. So that's something that you would want to consider. Moving on to direct RF type sampling solutions. This is the dream of most people sitting here. I would think hook up an antenna to an ADC, boom, you have all the RF spectrum you want, but it doesn't really come for free. This is something that would be meaningful for, let's say, really wide swaths of bandwidth. Let's say you want to do multi-gigahertz type digitization, and this is where it would come into use because you're running like 10 gigasamples per second converters, for example. You can choose the channels of interest to cut down your throughput requirements on your digital interface by having a DDC or a digital up conversion that mixed with numerically controlled oscillators. These are good for certain applications. Let's say you want to do hopping over multiple octaves of bandwidth and chirping or even carrier aggregation over 200 megahertz, 1 gigahertz even, let's say, and you have multiple channels popping in and out. This is something that you would consider. But what is the cost then? The cost is power. Converters, especially this fast, they cost a lot of power. Not just that, your dynamic range requirements with such a wide bandwidth ADC sitting there is crazy. So even if you have a gigasample per second converter and you have actually 12 bits, your ENOB turns out to be closer to like 9, which means a reduction in your dynamic range. So integrated transceivers, what are we talking about here? We're talking about devices like the 9361, which I propose are a practical zero IF solution. So why would you want to integrate a transceiver? Clearly, your size, weight, and power requirements go down. You burn less power. You don't have to worry about architecture scalability because now you can scale according to the small block that you can put in multiple places and create a 2x2 MIMO or an 8x8 or 64x64, whatever the case might be. It also allows for better partitioning, and I'll get to that in just a second. Now, with digitally assisted analog, you're able to run all of the things that we talked about, IQ imbalance corrections, within the transceiver, because now all of these things are sitting right there on a single chip, allowing you to make corrections at the source rather than later on upstream. Now, how is this done? Magic, or actually just good design. No inductors. The zero IF architecture helps a lot. It also reduces the requirement for band-specific RF filtering, and you're able to, and one of the reasons, again, why you can do this is because you can generate an LO at the 65 nanometer and lower node processes. So, I showed this diagram earlier. Now, to illustrate the point, with the 89361 or even the 9371, you have the AGC and the IQ corrections being done at the transceiver. What this allows you to do is get more of your processing power back at the baseband processor, So you could go ahead and solve the DARPA Grand Challenge if you wanted with that extra processing power, or do something else. But this allows you to do proper hardware-software co-design, and this is something that, again, that has come up. This is flexibility through partitioning, because you end up not having to worry about what happens here over here. Okay, so quickly, an overview of the 9371, which is the new transceiver, in comparison to the 9361. This is played here for quite a bit in one of the sponsor slides. Since no one pays attention, I put it up here again. So you all know what this is, right? Like, okay. Great. 2 receives, 2 transmits, 1 observation receive, 3 LO synths inside the chip, 1 clock gen, all in this 12 by 12 package. A very high-level marketing slide here. Clearly, the difference here is in terms of bandwidth. The added observation path that lets you observe the TX, 1 sniffer receive, which lets you sniff the spectrum at a completely different LO other than that is decoupled from your TX or RX LO, and LNA in front of it. Your dynamic range is higher. You have more bits to work with. The interface is now a JESD 204B interface, which runs high-speed SerDes. So you get, let's say you wanted to scale to a faster FPGA. This makes the case for using JESD 204B so that you can leverage some of the benefits of 204. Power consumption obviously goes up because now you have all the spectrum to deal with. Okay, I'm going to skip this. So the use case for the 9371 is clearly more of a multi-carrier scenario compared to the 9361. So you have a synthesis bandwidth of 250 megahertz as opposed to the occupied bandwidth of 100 megahertz. What that really means is you can put your channels of interest in the 100 megahertz around the LO, but you can synthesize up to 250 megahertz. The reason why we don't occupy all of the 250 megahertz because of all of the filtering stages that add a lot more gain variation throughout the signal chain. Also, 70 dB of image rejection as compared to the 45 dB. And this runs calibrations continuously in the background so that you keep getting the great image rejection as you put signals in and out. That is like this, for example. So a quick overview of the calibration changes that have happened over the transition from the 6.1 to the 7.1. Clearly, the QEC performance has increased. You have a wider bandwidth that you can play around with. You can receive on the RX or the sniffer, even on the ORX, but with some caveats there. We have a simplified AGC design as opposed to the 9361, which was sometimes buggy. Some people have complained, but TX LO leakage is better by 30 dB. This is great because now I'll speak to it in a future slide. You have the QEC tracking that runs every 30 seconds. The LO leakage runs every 2 seconds. This is something that you might want to consider if you're switching from the 6.1 to the 7.1 in terms of frequency agility. Also, the lack of maybe the fast lock profiles is something that you want to think about. Like I said, it's again about trade-offs. So internally, we do use the ORX data path for running some of these cals. Now, there are some other conditions that you need to work through, and if you read the user guide, you will learn that it's easy enough to set up. You might want to consider some of the reference software designs that we give you to design your system as well. Okay, moving on. So basically, in terms of all the calibrations that we do, it's improved a lot over the 9361. Now, the 9361 didn't have an observation receive, so you were pretty much stuck having to use one of the receive paths if you wanted to do any sort of digital pre-distortion type corrections. Power consumption is higher on the 9371 as well. Oops. Okay. Numbers. RX EVM. Now, this is a 64 QAM LTE signal, 10 megahertz wide, and this is not with anything special with like 10 capacitors sitting on my power supply or anything like that. This is just plug and play. Yeah. So 0.5% EVM, that is minus 46 dB. Now, why is this important? What does it mean, really? So consider that you have your minus 46 dB here at this minus 30 dB endpoint. That's great. 0.5% EVM is spectacular, but what if you had a lower signal value? Can you still achieve desirable EVM at this point or this point? Now, think about the sensitivity of the receiver. Think about residual EVM when you think about RX EVM. The 3GPP specs, for example, they call for a reference sensitivity level for different types of base stations. So for let's say 20 megahertz LTE, you have like minus 101.5 dBm that you need as a reference sensitivity level. And our customers would require even more margin to that spec. So you end up having to build transceivers that are going to beat any margin that you put it. So to show you again with respect to TX EVM, there is an actual requirement in terms of BTS conformance testing. Let's say you want to run 64 QAM, you need to be at least at 8% and or better, which is what customers really require. In terms of TX QEC, TX LOL, I don't see any images here because they're really 68 to 70, like 69 dBc below my signals of interest. Now, why would I care about these things? Of course, IQ imbalance argument applies here as well. But think about a case where, let's say you had really a strict spectrum emissions mask right here, then you would be in violation if your signal popped up or your images popped up here. So this really, what it translates to is reduced duplexer costs, because now you can run a smaller duplexer with lesser filtering as opposed to one that would have to filter out this particular band, undesired band here. And these are important when you're designing a system that complies to certain standards. So in this case, I'm getting like 60 dB image rejection, and my LO leakage, even though it doesn't look so great here, this is just one of the preliminary internal LO leakage cals. If you run the actual tracking cal with the whole observation receive, it pretty much goes down all the way down to the noise floor. Okay. I did mention about the ORX and the RX having independent data paths. So the ORX, let's say I was transmitting an LTE signal here. I end up seeing this guy on my ORX path, and this allows me to do like something like closed loop gain control or digital pre-distortion on the signal in real time. With the RX, I just looped it back from, instead of the ORX, I put it into my RX2 input here. What I want to show here is the fact that I can't even see my images. To compare with the 9361 and to say why this is different, so if the 9361 were given this kind of an input, you would see the images pop up right here, because it would try to optimize maybe only for this particular signal that will land here, but may not optimize for this guy because it's really looking for the highest power signal. The 9371, on the other hand, actually does a true wideband quadrature error correction. And this is true over temp. So again, real system considerations, not some numbers being thrown around in the best lab conditions. Okay, I'm almost done here with the AGC. Really is the same. This is a SIM-RF model for the 9361 AGC. You still have pretty much the same sort of action. The gain control happens at a single block, but can affect the front end, can look at the power level in between after one of the HB2 filters, and decide when to attack and when to recover. One of the main things to note is the fact that you don't have an LNA in the 9371. Also, the gain delay calibration lets you be agnostic to gain changes. So this is what you would get after the gain delay calibration is done, and you wouldn't see this gain change. That's mainly because of timing differences between when the digital gain kicks in and the RF gain kicks in. It's much more linear, runs a bit slower, but it is more accurate, less buggy, of course. So it's a much more simplified AGC design. Now, again, coming back to my argument about the partitioning and putting the AGC in the transceiver instead of the baseband processor, you have to imagine a case where your interferer pops up every now and then. By the time you see it at the baseband processor, it's too late to combat it in the transceiver, and you've lost a few dozen frames already. So the AGC on the 9371, for example, kicks in on the order of 4 microseconds. This is compared to what a baseband processor might take a few milliseconds. A few milliseconds in LTE world is a few subframes, just for comparison. So how do you get your hands on with these toys now? Of course, you can use your GNU radio blocks, VIO device sources and sinks. The 9371 sources and sinks are in the works, so you should be able to get a little bit more access into that soon, as you did with the 9361. So you could go ahead and prototype your modem stack on GNU radio. You can also do your full system development with the API and the kernel drivers if you wanted to. The links to all of these, so all of the references are in my notes on the PDF, so if you want to look through them, you can definitely find them. Simulation in the MathWorks environment is possible with SIM-RF and SimLink. The 9371 models should be out in some time. I don't know when, but they're currently in the works. This lets you evaluate the entire system in a simulation test bench rather than having hands-on the hardware itself, although I would recommend getting the hardware. So to conclude, many RF challenges that plague a systems architect. You need to choose a radio architecture that matters to you the most in terms of the design trade-offs. Partitioning and distributed intelligence, and intelligence here means different sorts of accelerators. Even if it's digitally assisted analog or whatever it may be, you can imagine a case where there are throughput bottlenecks preventing, or latency bottlenecks preventing you from choosing one type of architecture or the other. Now, we do have a lot of products. Integrated transceivers themselves make a good solution to some of the low-cost, easily prototypable solution or problems that you guys face in terms of SDR and software-defined radio. All right, I think that's all I have. Opening up for questions. You can also find us at booth 12, that's ADI, or you can find some of the products that use the 9361 or the 9371 at all of these booths. These are the confirmed sightings. If you find more, let me know.
All right, do we have any questions for Sham? One in the back?
Is that 300 megahertz lower limit a hard limit with a synthesizer, or can you go below that with a reduced performance, like you can with the 61?
So for the 9371, yes, the 300 megahertz is where we spec our performance. Whether it is possible that we can go down below 300 megahertz with reduced performance is something that we would have to test further. If you want to know more, come talk to me. We can discuss that. At this point, that's kind of a hard limit.
All right, right here, Jose.
Thanks for the presentation. Really excited to see some of the updated performance for the 9371. But with the like a 3 to 5x power increase, it seems to me like maybe the 71 is targeting different markets than the 61. So I was wondering if you could talk a little bit about the long-term support plan for 9361 versus 9371. Is there going to be phasing out, or how are you going to handle that going forward?
So the 9361 is currently supported by our engineer zone. So if you have questions, you go on and ask them. I think that support model continues forever, I guess. The 9371, yes, you're right, it burns a lot more power. It is a different device. It is targeted for a different type of audience or different type of market. Mostly, again, in the cellular comms infrastructure market. You can imagine the 9371 being useful for small cells or picocells, if you think about it. Yes, what you do have is higher power dissipation, but what you get is more bandwidth. And you can't get more bandwidth without spending a little bit more on power. And the fact of the matter is it's a lot of hardware inside a single chip. And even cooling it, I mean, if you saw the figure, the package itself is different from the 9361. It's a sort of a flip chip with a substrate so that you can expose the die directly and kind of, resolve heating issues a lot better than the 9361. So you could potentially turn off a few of the components within the part to achieve lower power, but that is, a little bit of an advanced tweak.
Yeah, but just to follow on, 9361 is going to have a very, very long life. So there's no issues about that. It's designed into contractual obligations for long life in some of these programs, and it's going to be around for a long, long time.
Is there going to be a follow-up or any revision of the 9361 that integrates some of these updates?
Yeah, there was the question was like, is there going to be a new 61 coming out, maybe like lower power, similar bandwidth? There will be a part coming out be announced, I think, in the November, December timeframe.
And there are more updates to the 7X series of transceivers either.
Last question.
Does the MATLAB Simulink environment support the 9371 now, or is there stuff that's pending coming from analog devices for that support?
In terms of libIO and IO devices, I think Robin would answer that. I think it is supported, but in terms of the SimRF model, it's currently in the works. So maybe in a few more months that should be available.
Okay, thank you.
Is that what you were asking?
Yeah, yeah.
Right.
All right, let's thank our speaker. Thank you, Shyam.
All right. Thanks a lot, guys.